sheet, you should see 3 numbers. And so all of my tests will have multiple choice section, okay, and they're each worth 1 point apiece. The vocab's worth 2 points apiece, and the short answer are worth 3 points apiece, which just kind of how it turned out this time. So the first question, who discovered that Jupiter has moons? Galileo. B is the best answer. For 2, if a part of the full moon passes through the Earth's umbra, just a part, then we would call that actually a partial lunar eclipse. C is the best answer there. Question 3, which of the following does not use the term light year in an appropriate way? Light year, of course, is a distance, so A, B, C, and D are correct, but E is incorrect. It's incorrect to say, use it as a time. It will take me light years to complete this homework assignment. So E is not correct. Question number 4. Going down. All right. Which of the following statements about circumpolar stars are true at all latitudes? And this one threw some people off, and people tended to put A, that we know that circumpolar stars would be close to Polaris, but actually, if you're at the North Pole, all stars are circumpolar, and they're not close to Polaris. So the best answer there is that by definition, they're circumpolar. B, they remain above the horizon. Question 5, how did Eratosthenes estimate the size of the Earth? And remember, he actually had 2 locations, and he knew the distance between the 2 locations, and he looked for the angle of the sun. So that A is the best answer there. Question 6, the fact that virtually every galaxy is moving away from us, and the more distant galaxies are moving away faster, we conclude that B, the universe is expanding. Let's see if this will work. Good. What causes that backward or apparent retrograde motion of the planets? The best answer there is C, that as Earth passes another planet, the other planet appears to move backward with respect to the background stars. It overcomes it. Question 8, what makes Polaris so special? E, that it is very near the North Celestial Pole. Question 9, how long does it take the sun to complete one orbit around the center of our galaxy? That's 230 million years. 10, he discovered that the orbits of the planets are ellipses. Of course, that's Kepler's first law. So Kepler, A. Question 11, the principle of Occam's razor, that was the one I called keep it simple, silly, states that B, in explaining a natural phenomenon, the simplest explanation is the best. Question 12, which of most of the mass of the Milky Way galaxy is located A, in the halo region? We'll be coming back to that later on in the course. Question 13, if we look at a photograph of many galaxies, assuming that they all formed at the same time, which one appears to be the youngest? And the best answer there is C, it's the one that's farthest away, because it took that long for the light to get to us. It will look the youngest. Question 14, say you're standing on Earth's equator, whereas Polaris, that would be directly on the horizon, the northern horizon. Question 15, if you experience nighttime when, the best answer is D, the side of the Earth that you occupy is facing away from the sun. Question 16, if you locate the North Celestial Pole, how can you determine your latitude? And actually, C, it will be the altitude of the North Celestial Pole. Question 17, why did Ptolemy have the planets orbiting on those little epicircles? That was D, to explain that retrograde motion. So D is the best answer. Question 18, has Polaris always been the North Star? Nope, because of precession, right? The Earth's axis is slowly changing the direction it points to. Question 19, why is it summer in the northern hemisphere when it's winter in the southern hemisphere? The best answer there is C, that the northern hemisphere is tilted toward the sun and receives more direct sunlight. Question 20, on a cosmic calendar, compressed into 1 year, when did the dinosaurs become extinct? E, in late December. Question 21, that sun dagger in New Mexico, it pierces the center, D, at noon on the summer solstice. Question 22, Kepler's second law states that planets moving around its orbit sweep out equal areas in equal amount of times. That basically means that D, a planet will move fastest at what we call perihelion, when it's near the sun, and slower when it's at aphelion, farther from the sun. Question 23, if you see Polaris directly overhead at midnight, you must be visiting Santa Claus, be at the North Pole. Question 24, the distribution of mass in the Milky Way galaxy is determined by the motion of the stars, or the rotation of the stars in the galaxy. So those are each worth 1 point apiece. And then on to, now these were each worth 2 points apiece. In some cases, I went ahead and gave you partial credit. So I was after precession for question 1, the process in which the Earth's axis of rotation is undergoing a coning motion. Question 26, I was after galactic recycling, but I think if you put star recycling, I gave you 1 of 2. For question 26, the process by which stars live their lives and they create heavier elements and then they return their material back for other stars to be born. Question 27, I was really after zenith, but I didn't like the way it read, so I definitely would take meridian too. The location, it should just say directly. The location directly above your head in the local sky is called your zenith, or meridian. So it's called your zenith. Meridian goes from due north to due south through the zenith. Question 28, I was after apparent retrograde motion is when the planets appear to go backwards. Question 29, I was after the ecliptic plane, but I didn't like the wording of the question. I must have gotten in a hurry. It says that the Earth orbits the sun on the, and then I was after the ecliptic plane, but I would take some sort of form of tilted axis. So if you got that and I counted it wrong, let me know, because I gave at least, I think I gave full credit for that. Question 30, the angle an object makes in your local sky with your horizon is called the altitude. Question 31, I was after astronomical unit as the average distance between the Earth and the Sun. Question 32, the terminator is the line on the moon where the dark part of the moon and the light part of the moon meet. And the last one, hypothesis, is kind of your best guess in the scientific method that explains your observations. So this next one, we're each worth 3 points apiece. Now remember, checks means you got it totally right, okay? And if you didn't get totally right, I wrote out next to the side how many I took off. So 34, I wanted you to kind of tell me what you know about a light year, that yes, it is a distance and not a time. So I kind of wrote the star and little photons taking a year to get to the person, and that star is 1 light year away. Question 35, I was after you to tell me how you can find Polaris using some stars. And if you went ahead and put down Big Dipper and something like that, but you said you used the handle of Big Dipper to find Polaris, I went ahead and took off 1 or 2. I can't remember. I was consistent because it's actually the bowl stars in the Big Dipper that help you find Polaris. And there was a couple people that actually wrote the little picture just like I did. I'm like, oh, that's so adorable. Question 36, what's Kepler's first law? It describes the shape of the orbit of the planets as ellipses with the sun at a foci. Question 37, of these 6 ways that we're moving, you needed to give me 3. The Earth is rotating, the Earth is orbiting, the sun is bobbing up and down, kind of within a group of stars. Number 4, the sun is actually orbiting the center of our galaxy. Number 5, the galaxy is moving away from other galaxies. And number 6, the fabric of space and time is actually expanding and carrying us along as it goes. Question 38, explain why we here on Earth only see one side of the moon. We call that the near side of the moon, the side that we see. And that actually is because the moon is in sync with its rotation and its orbit about Earth. Some of you kind of said something about Earth's orbit, and it has nothing to do with the Earth's or the Earth's rotation. It's the moon. Okay. Then the last one, you need to give me 2 ways in which Galileo, with regard to his observations, helped solidify the whole sun-centered model of the solar system. And so I put a bunch up here. So he was a busy guy. I think somebody, I don't know if it's this class or my other class, put that Galileo saw not only Jupiter, he saw the moons orbiting Jupiter, but he also saw rings around Saturn, and that's true. He actually called them like ears. He thought that here's Saturn, and here's a ring, and they look like little ears around Saturn. So that's adorable. Okay. So that's that. And so those are for you guys to keep. On to dun dun dun. When galaxies dance. When galaxies meet. So these actually, not all galaxies look this pretty to us. These are what we call face-on images. Okay, so basically they're frisbees, but you're seeing them face on. And you can kind of see the hard cores in the middle. Okay, those are actually supermassive black holes in the middle of each one of those galaxies. The point of Chapter 4 is gravity. One of the major points about Chapter 4 is gravity. And can you almost kind of see them dancing? They're kind of the gravity that pulls those galaxies together is the same gravity that makes things fall. Okay, I just am amazed at that. I'm amazed and appreciative of that. So actually, it was Isaac Newton that came up with a mathematical equation to talk about that gravity. Okay, Isaac Newton. But I believe before he came up with this whole gravity thing, an equation, a mathematical equation for gravity, he came up with what we call laws of motion, 3 laws of motion. And you might have heard them in other classes. So we need to talk about Newton's 3 laws of motion that dictate, remember we said in your test, a test question that how do you know where the mass is in our galaxy? Well, you watch the motion and you apply Newton's laws. Okay, so in order to intelligibly talk about motion, we need to kind of get some terms under our belt. So when something moves, it relocates from point A to point B, we can describe like how fast it was going, its speed. So what we would do is basically take the distance from point A to point B, okay, and we would divide by the time it took to get there. That's speed, okay. You're going down the road at 30 miles per hour. In 1 hour, you'll go 30 miles, okay? That sort of thing. That's speed. There is kind of, and we use them interchangeably, but we really shouldn't. There's a slight difference between speed and velocity. What velocity does is not only says how fast you're going, distance per time, but it says what direction you're going. And that's important. Velocity, what direction are you going? So, velocity is what we call a vector. I like that word. It's kind of growing on me. Okay. So in physics, we can show vectors with arrows. So for instance, if I do an arrow like that, okay, compared to an arrow like this, okay, I could say that they are both going north, okay, and this could be 10 miles per hour mph, and this is 20 miles per hour. Okay, so the length of the arrow gives me what we call magnitude. Okay, but the arrow definitely gives me direction of the velocity. I could go ahead and change up, and I could go the same length as that middle arrow, okay, but change the direction. So to me, this looks like 20 miles per hour. What do you think, kind of northeast? I'm thinking so. Okay, so we need both kind of a magnitude of what was speed, and we also need direction to give velocity. So the last thing we need to talk about, Newton's law is actually his second, maybe even more than that, but Newton's laws of motion talk about acceleration. Okay, now if I were to ask a kid about acceleration, he'd say, oh, I know. Say like when mommy sees a yellow light, she pushes on this pedal in her car. She calls it accelerator. No. So really, we think about hitting the accelerator in our car. Makes us go faster. But acceleration is a change in velocity. Okay? And velocity has 2 components. So, in other words, you can change, okay, if you're talking about acceleration, okay, if you change either the speed or the direction of motion, then you have accelerated. Change speed and or change direction, and voila, you have accelerated. So with that in mind, here we have a car doing a few things. We can call this, little example A, B, and C. And if we focus on A, you see that the car went from 30 kilometers per hour to 60 kilometers per hour. It went faster. Okay, so in that case, and in physical science, we use this triangle. Actually, it's the Greek letter delta to mean change in. Anytime you see that little delta. Okay, so actually in this case, we have a change in the speed, right? Change in the speed. Let's look at B right quick. Notice that with regard to up and up speed, that car doesn't change. Speed doesn't change, but the direction does. I'll show you. If we wanted to say, for instance, snapshot, I'm going to go ahead and take an arrow and kind of go down the middle of the car. Okay? There is the direction that that car is going, 60 kilometers per hour. I'm going to pick one here. I'm going to put an arrow down the middle of the car. Okay? So here he's going, gosh, we call this northeast, maybe. And here he's going east. He's changing his direction. Still going 60 kilometers per hour. He's changing his direction. Let's kind of finish that thought over here. Wow, looks like he's going kind of southeast. Okay. In this case, he is changing his direction. Okay, so that is a form of acceleration. All right, so keep that in mind. Then this last one, actually slowing down, going from 60 kilometers per hour to 0 kilometers per hour. We would call that deceleration, okay. And actually that mathematically is negative acceleration. So, all right, so acceleration is important. So if you would, you're going to want to go ahead a few slides and find this slide. So we're going to talk about Newton's 3 laws of motion. Looks like it's at the bottom of page 42. And again, you've probably heard these laws before, but just bear with me. Newton's first law says that an object moves at a constant velocity unless a net force acts to change its speed or direction. Okay. Hey, we just talked about changing speed or direction. What do we call that? Acceleration, exactly. Exactly. So, the example I have, it's easier to talk about, I think, this law of motion if you go to outer space for a number of reasons. One is in outer space you don't have any air to kind of mess up your experiment. Okay, so the thought here is that once we get this object going, okay, with a certain velocity, I'm going to put the letter V up here. This cute little shuttle thingy, I don't even know what it is. Okay, he has a certain velocity, V. And he's going, looks like he's going that way. He is going to keep that velocity, okay, going that same speed in that same direction forever, unless acted upon by some other force. That's Newton's first law. The reason we go to outer space to do this, quite frankly, is that, for instance, if I take a force and I throw something, okay, it's not going to keep going forever, is it? No. Because of probably two things. One is gravity, going to make it fall down to the earth, and kind of related to that, when it hits the earth, then we have friction. So you can't really do experiments like this. But here's another one for you. It moves at a constant velocity. So is zero velocity a velocity? Yep, it's just zero. Okay. So the thing is any object with zero velocity is going to keep that velocity, okay, unless you give it a force. Okay? I know it sounds kind of obvious. Before I leave this slide, there's one other thing about this slide. We're going to talk about something called momentum coming up. I don't know if we'll get to it Friday or today. But related to momentum is inertia. Inertia. And sometimes Newton's first law is called the law of inertia. And inertia, basically, an object has inertia based upon its mass, not its weight, but its mass, okay, and its velocity. So objects with zero velocity have inertia based upon their mass. Objects that are moving, okay, have a certain amount of inertia based upon their mass and their motion. The law of inertia is really cool because the law of inertia, or Newton's first law, an object at rest will remain at rest unless acted upon by an outside force, is the reason why, if you're really good, but you can like pull out something from underneath something else. This pen has a certain amount of inertia. It wants to stay where it is. Okay? If I do it quick enough, okay, the inertia kept it where it was. Okay, so that's inertia. All right, and it's kind of related to momentum, I think. So Newton's second law of motion goes like this. Remember I said acceleration was important. We kind of talked about acceleration before we talked about Newton's laws. So acceleration, remember, is a change in velocity. So acceleration could be a change in speed, or it could be a change in direction of motion. Change in direction of motion is also acceleration. So this actually is a player in astronomy, because if we look at Kepler's first law, which you told me is basically saying that the planets orbit the sun in the shape of an ellipse, right? And go back to the car a minute ago. We saw the car kind of curving. We said that car was accelerating. Okay? And so also the planets are accelerating. The planets are accelerating as they orbit the sun. I don't care. I don't even have to go out and clock them. I just know they are because they're changing the direction of motion. And of course, later on, Newton said what that force was, and that actually is going to be the force of gravity, F sub g, force of gravity, that is causing that acceleration. So this is kind of cool. We said, according to Newton's second law, if you apply a force, you can look at it a couple of ways, but if you apply a force, okay, and you know the mass, you can anticipate the acceleration that will occur. Okay, you apply a force, mass isn't going to change, it will have a resulting acceleration. So the example I have here, I think it's from your textbook, is throwing a baseball. So basically a certain amount of force is applied to that ball with a certain mass, okay, and it results in it going from 0 meters per second to a certain meters per second. Okay. Have you ever gone to Adventureland where they gauge how fast the ball is being thrown? Or wait a minute, you're supposed to throw a ball and guess how fast it's going to throw, or something like that. It's over by the, anyway, by the big roller coaster. Newton's third law goes like this. For every force that's applied, there actually is another force that is equal but in the opposite direction that's also going on. This is the one where I kind of say, if you have kids and you say, if you hit your brother's going to hit you back. That's kind of like for every action there's an opposite and equal reaction. And so the example here is, looks like spacecraft going into orbit. So what this looks like is, we're going to talk about energy later on, okay? But basically, in here, they have fuel. And they have used their fuel they are burning their fuel. And some sort of chemical reaction. RXN, okay? And that chemical reaction is causing a flood of material to go down this way with this force, and it's resulting in what they want to happen is a force to go in the opposite direction with equal magnitude. So those are your two forces working there. All right. So now back a few slides before. So like if you drop something like a pen or something, you know it's going to fall, and you may not be able to detect how fast it's falling, but if we could clock it, it actually is going to fall faster and faster and faster and faster and faster. It looks like it's just one speed, but it starts here and it goes faster and faster and faster and faster. And how much it accelerates actually is a function of the Earth, okay? The Earth's gravitational pull on objects, and actually it's independent of the mass of the object. It just basically, the force of gravity associated with the Earth accelerates objects 10 meters per second for every second it falls. So it looks like this. So whether it's a pen or whether it's a bowling ball, okay. Now there's a big difference, for instance, though, between dropping, the mass doesn't matter. There's a big difference, though, between dropping like a bag of feathers and a bowling ball. You might be like, well, I know the bag of feathers is not going to fall as fast as the bowling ball. And here's the catch. Remember I said that experiments are better in outer space? Okay. The problem with dropping something on Earth is we have all these gas particles that create a drag on feathers that doesn't create on the bowling ball. But in theory, if you were to go to the moon, in fact, one of the Apollo missions, that's what he did. He basically went to the moon, and it wasn't a bag of feathers, but he took a feather, an eagle feather, quite appropriate, and he took a hammer and he dropped them on the moon. And you would think that this would just float down like on Earth, but that's because of air resistance. They actually, without air, hit the moon at the same time. Okay, so that's kind of how that works. Now, the moon's acceleration would be less than the Earth's acceleration. So on Earth, you figured, you might have learned it as 9.8 meters for every second. That's how I learned it. But if you round 9.8 up, you do get 10 meters per second. So the way this works is in 1 second, its velocity. If we were to track how fast it's going right there, 10 meters per second. We let it go another second, and now it's going to go 10 plus 10 or 20 meters per second. Okay, it's going to go faster and faster. If we were to go down here, time is equal to 3 seconds. Let it go another full second. You figure it's going to go 20 plus another 10 equals 30 meters per second. That's it. Okay, if it's doing it without air resistance. So I think your textbook might address this. Because of air resistance, actually, if an object's falling, it maxes out at what we call terminal velocity, and that's because of aerodynamics. So basically, it won't fall any faster. It's done accelerating. Okay, but that's only because of air resistance. So regardless of the mass of the two objects you drop, we should try this. I'll have to think. They will hit the ground at the same time. That's a good place to break for today. And we'll pick up on the next slide, force and momentum. Still trying to think, how could you test that? Yeah, you need something high up. There's been this